Questions 6 to 9. So they give us a certain pharmaceutical compound X and showing how it decomposes when it is dissolved in water. Okay, so they show you the diagram and the time taken for the concentration of compound to decrease to half its initial concentration is the half-life, T1 half. Hopefully you knew that already. And so we go on to the question, which of the following is the best estimate of the amount of X that decomposes in the first 100 minutes? So how much X decomposes in the first 100 minutes? So we look at the graph and we look at 100 minutes and we go up to the black dot at 100 minutes. We just have to, try to get comfortable as possible with graphs. And you see that the box, the line, the horizontal line on the box goes at 0.02 and 0.04. So you can just draw, put a little mark at 0.03, which is, halfway between 0.02 and 0.04. And then you'll notice that the black dot is pretty much midway between what you just drew and the line for 0.02. And so that would indicate that it's at about 0.025. And if it's at about 0.025, when you started with 0.1 minus 0.025, which is where you're at, so that will give you about 0.075. And all our units are okay. We're checking, yep. And so that's how much would have decomposed because we were left with 0.025 at the end. So that's a reasonable estimate. And next, question 7, which of the following is the best estimate of the value of T3/4? So, I've never seen T3/4 written that way. I've never seen that. But they are asking for the value of T3/4, so the time for the decomposition of X. So I'm going to have to assume that they mean that the time that it takes for 3/4 of X to decompose. That has to be my assumption. I must admit, if I saw a bunch of questions like this, I would probably start changing assumptions because the question seems a little too, a little cheeky, And so anyway, and we just finished doing that on top of this because at 100 minutes, we know that that's when 3/4 of it has decomposed because obviously 0.075 out of 0.1 is the same thing as saying 75%. And that means 75% has decomposed, which is 3/4 at the 100 minutes mark. So I guess you just have to, accept it. I guess because the way they wrote it, that it's T3/4 for the decomposition. If they just wrote T3/4 without for the decomposition right away, I don't know what I really would have put as an answer because they defined half-life as decreased to half of its initial concentration. So why wouldn't T3/4 be decreased to 3/4 of the initial concentration? So, but anyway, I would take it just because they the wording in the question. So 7, the answer is C, and moving along. Question 8, which of the following is the best estimate of the rate of the decomposition of X, again, for 30 minutes after the solution was made? So the rate after 30 minutes. Okay, so as soon as you hear the word rate, of course, you should be thinking of something per unit time, something divided by time. Because that is the meaning of rate. And there are many ACER problems and questions that surround your comfort with that. And for the graph itself, we have moles per liter over here, which is molarity that I'm just putting a capital M for. And then we have time down here. And so the curve does something like that. Okay. And so looking at the curve, if I know that it's molarity over time, that's how I can get a rate. So by having m over t, and so m over t, the way I can get that information is obviously I don't get moles over time if I multiply this by this. That won't do it. I have to be able to divide in order to get moles over molarity over the time. So multiplying this by this is where you get the area under the curve. And sometimes getting the area under the curve is helpful, but just check your units to make sure that by multiplying this times this, you get a result by looking at your units that is useful to solve the problem. And of course, you just look at the units of the answer choices that are given to you. But this is not the case here. Area under the curve won't help us here because we need per unit time. And per unit time, we get that by rise over run. You know, you could remember that from your high school times, rise over run, which means delta y over delta x. In other words, it is the slope. And of course, by having delta y, which is the molarity, over delta x, which is the time, we get the rate. It's something per unit time. Perfect. So that's what we're looking for. Now, so all we need to do is to find the slope at the time that we're given, which is 30 minutes. And you'll find that 30 minutes is somewhere here on your graph. So you need to find the slope at that point. So it's pretty simple, you know. Basically, all you're going to do, and you do this in the exam, is that you look at where 30 minutes intersects the line like this, and then basically using your pencil. You're not going to use a ruler in the exam, but you just use your pencil, and you just let your pencil rest so that it's tangent to the curve. You notice that? I cannot put my pen like some kind of strange angle like this, okay, where it's crossing over some part of the curve. I can't put it like this either, because you could see part of the curve at the bottom of the pen. I have to place my pen exactly at an angle which is tangential to the curve like this. And then once you do that, you just have to read what you can read on the X and Y axes. And I think that if you do this, this is what you'll find. Just very carefully put it like that, then you'll find that the top number up here is at pretty much 0.095. So I would write 0.095, and that's of course moles per liter. And so it's delta Y, but it's this minus 0. So delta Y is just the Y over there. And then you look at where it intercepts on the x-axis, and I believe that when you do that with your pencil or pen, you will find 100 minutes. And so once you've done that, you have the answer. You just have to go, this is 10 to the 2 over here, and then that's 1, 2, minus 2 up there. So you have 9.5 times 10 to the minus 2 on top. You have 10 squared at the bottom. So this comes up, and this becomes 10 to the minus 4. So you have 9.5 times 10 to the minus 4. And so the answer is C. And you notice with the unit, this is moles per liter per minute. And that is the correct units. Always an extra check to make sure that you did your work properly. Moving on to question number 9. So, is the decomposition of X a first order reaction? Well, the first thing that you need to understand is what is a first order reaction. And the first thing is you should be very comfortable with the shape of this curve with these units. This is molarity, this is time, and you just have to imagine for yourself. You have a bunch of chemicals, that are reacting with each other in a solution. At the beginning, you have many of these chemicals that are there. You put them in, then they start reacting. As the reaction proceeds, you start having more and more product, of course. But think about it. at the beginning, right at the beginning of the reaction, you have lots of reactant. So they're interacting a lot. But as the reaction proceeds, you have less and less reactant, less of the beginning stuff. So you have less and less of the reaction taking place. This is very normal. This is a very normal first order type curve that takes place. Now you might have in your mind, but I thought a first order reaction is linear, and you might correctly remember the rate law, that rate is equal to k, and in this case, this is the concentration of X over here. And so we have something like this. And then this would be a first order reaction because the exponent is 1. And so isn't this linear relationship between rate and the concentration? But no, it doesn't work that way. In fact, the concentration, this is exactly a first order reaction. And the way to make this linear is simple, and this is a frequent exam question that ACER likes to ask. It's you need to take the logarithm, because that is the purpose of logarithms. The purpose of a logarithm is to take an exponential curve, this one's descending exponentially, and then turn it into a straight line, or to take a curve that is ascending exponentially and turn it into a straight line. This is what logarithms do. This is a exponential curve, and this is a logarithmic curve that is controlled. The speed of increase is controlled by the use of the logarithm. That's the purpose of it. So here we have a logarithm, which is the natural logarithm, ln x, and this is a first order reaction, and this is time. And in fact, this slope is obviously a negative slope. It's going down, and it's going down in a very constant way. So this is actually negative k, and that is a constant. And so for the first order reaction, this is a type of question that comes up regularly often. And the other thing is that because this is constant, we have that the half life is also a constant for first order reactions. So these are important points to keep in mind. So is the decomposition of X first order reaction? It says no, the plot in the figure is not a straight line. Well, no, it is not a straight line, that's true, but it is still a first order reaction with a curve thing. And it says, yes, the plot in the figure is a curved line. Oh, interesting question. Because this is a first order reaction, but look, that's a second order reaction. So a second order reaction also has a curved line. So answer choice B does not provide anything to be able to specify that it is a first order reaction. Then it says no in the first 20 minutes, blah, blah. And then it says yes, the concentration decreases to this and that. So basically they're trying to see whether or not the half-life is constant. And if you look, the concentration decreases to 0.5 in the first 50 minutes. So that means it decreased by half-life in the first 50 minutes, and then to 0.25, half of that in the next 50 minutes. Perfect. So that means the half-life is constant. It was reduced by the same amount, half, in the same period of time, 50 minutes. And that's what makes D the correct answer. And if you wanted to read more about reaction rates, you can read about it in Chem 9.1 to 9.4 in the new edition of the book, and half-lives in Physics 12.4.